we talked about last time, we basically took our ideas of motion of like a big mass, moving in gravity and moving with springs, and we said, what happens if we shrink that down to the molecular level? And so what would happen if we imagine a potential well that looks like this? Because there's a molecule here, say that's fixed, not going anywhere, and there's a molecule here also, and this is, as always, some energy, whatever that means, right? So I told you before, it could be the chemical potential energy, would be what we would normally call it. So what this kind of looks like is how two atoms or two molecules might stick together, right? When they come, they bond, form a bond, so the energy is lowered by atomic or electronic mechanisms. But what's different is, if this was a big classical ball rolling mass thing, if you rolled it in, then it goes down to here, left kinetic energy, and it will roll out. So what's different in the molecular scale is everything is always interacting with the environment and exchanging energy and losing energy with the environment. So you have essentially like friction. You know, in the macroscopic world, if you slid that down, it wouldn't get all the way out. Because of friction, microscopic world, same thing. Everything is always jiggling and bumping around. We had a video of it that we'll need to look at a couple times here. So this was the video of Brownian motion of little particles of milk. If you just look at little particles of milk in a microscope, you can see them bumping around. And you would think that's probably just vibrations or something to the building, but that's actually the molecules bumping into the milk particles. So you probably looked at that at some point in a microscope. But that little jiggling is the reason this thing speeds up as it goes down this hill. It gains some velocity this way, but it quickly collides into things. The net velocity this way is just distributed, and it loses it. So in the end, you really would just have something sitting there, and it would be bonded in some way or stuck together. But then, let's see, so that will write the bullets. We'll just talk about okay, so this is kind of like two things sticking together. It loses energy to sit there. But the third and the critical part is, in addition to losing its energy by interacting and shaking around, it also continues to interact and shake around. So I was representing that like that, little vibration marks. So it's bumping around, sitting there at the bottom of the well. Therefore, as it bumps around, it's actually going to slightly higher energy and slightly lower energy. It's not just sitting at one energy level. So that's basically all we need for translating our simple intro mechanics ideas to the molecular scale. And then what we talked about a little bit also was, okay, therefore, if we think of my little vibration marks as quantitative, really telling you exactly what energy range it goes through, and if you have something sitting in the bottom of a very deep well, and there's the energy range, it's not going to get out. But if you have something sitting in a very shallow well, and here's the energy range, it might get out. Right? Something might bump it enough that it gets back out. And we talked about the formula for predicting how fast that would happen. So I won't write it down, we'll use it again. Use it again when we do chromatography. Okay, that's where we were. That was all we had. So now what we're going to do is we're going to make our toy model of chromatography. The thing they use to separate molecules. I think that I defined something, just as a reminder of what it does. Flow sample through tube. Flow sample, which is of course a mixture of molecules, through a tube with sticky pumps. Okay, so a lot of our reason for talking about this and what happens to molecules in these wells is we're trying to explain what sticky means. Sticky in terms of physics. How do we describe it? That's how we describe it. Okay, so now we're going to draw our little toy model of chromatography. Right? So like this. Here's the tube. And it's got the little sticky parts, kind of like that. This is the non-quantitative numbers. It's just a picture of parts. Right, so we send our sample in here. And we see how long does it take to come out of here. Chromatography. So simple. What we can now do is draw the energy diagram chromatography. Okay, here we go. In this case, yeah, horizontal is the x-axis. So I've almost just said the x-axis is the x-axis. If you still do it even at my age, you still think of it as the x. And this is the energy. As always, vaguely defined. In this case, we kind of mean potential. Okay, the fact that it's flowing means you don't have to get into the fluid physics of it, but there's pressure, higher pressure on one side than the other side. That's what's pushing it along. So your energy would actually be kind of like a line going down because there's a pressure difference causing flow. And just like a ball would roll downhill, the liquid or the gas flows through the tube. But what we have is everywhere it's sticky, we have a little well like that. So this would be, I think, the energy diagram of chromatography. Never been done before, but I can't find it anywhere online. I had to make all this stuff, okay? The energy diagram of chromatography. So what happens then is your molecule comes along, and it's rolling down, and it gets stuck here. But then eventually, it vibrates out of there, and it gets stuck here. Eventually, thirdly, it makes its way out of there, and it gets stuck here, and it gets stuck here, and eventually it makes its way out. So what we're measuring in chromatography is the retention time. How long did that take to do that whole process? Get stuck in a well and get out of a well. Next well, next well, next well, etc. So that's like the idea of chromatography. So now the question is, what does a toy model mean? Okay, so we're going to make, this is what physicists do. We're going to make a toy model of chromatography. What that means is we're going to kind of just put some numbers together and see if we get something that makes sense. And then if we were really doing like new science, we would use our whole numbers and formulas to see, is chromatography good? Is it going to work for this kind of a thing? Or do we need to change something or what? We'll start with just setting up a toy model. Okay. So typically you're flowing this through a tube, and I've seen these tubes before. You know, they're little. So we're doing orders of magnitude. Little is a millimeter. Okay? So our tube, see a toy model. Our tube has a 1 millimeter by 1 millimeter cross section. That's the area. Oh, I forgot. Oh, I got ahead of myself. Yeah, okay. That's coming in a minute. There's one more thing. We have to talk about physically what's happening here with these things. Right? Eventually, we're going to have to say, what does sticky mean? How deep is that well? Remember, a really deep well, molecules never going to come out. Really shallow well will actually blow right by. So we must have a well that's kind of deep. So what we want to do is base that on like real chemical properties. Okay? So let's think. So what does sticky mean? Now we're going to get more detail. We have 3 kinds of sticky. And then we'll do the toy model. Okay. First kind of sticky is, well, sticky means weak molecular bonds. So we're going to talk about 3 types. All right, in a loose way. The first is electrostatic. So we touched on this briefly when we talked about the electric field and charge. I mean, we didn't really obsess with it. But if you have a couple of molecules, here's a molecule, and here's a molecule, very roughly, and this one has a little bump on it that's positive. It's a carboxyl group or something like that. When hydrogens come off, so oxygen is just positive, but an amine group anyway. You have a chemical group that's positive here, and a chemical group that's negative there. What would happen is they would both feel an attractive force because opposite charges attract, which we may have said. I'm sure we would say that. We mostly talked about fields. But, oh no, I showed you the thing of the Teflon, right? So like charges repel, but opposite charges attract. So 2 charged molecules, so what you could have is your molecule here flowing around is charged positive, and maybe your little sticky spots you designed to be negative, and that's why they would attract. So, fine. So, how deep is the well? So in this case, it's about 4 to 80 kilojoules per mole. Very approximate, okay? So it depends on a lot of things. How charged it is, how close the parts can get together, what solution it's in. But typically that rough value. And also, as we said last week, the amount of the jiggling is 2.5 kilojoules per mole. So that's bigger. Doesn't mean it'll never come out, but that is bigger. Okay. So electrostatic is 1. 2 is the hydrogen bond. Okay, so hydrogen bond is when you have, like, say we have our cholesterol molecule with its 4 rings and a tail. Remember, it has that OH at one end of it. That's what makes it an alcohol. It's cholesterol. So it has OH there, and then maybe another molecule comes along, a lipid with an oxygen like that. We call that like a carbonyl. Okay, so the hydrogen kind of has a propensity to go jump over and to be attracted to that oxygen. Okay, so hydrogen is special in a sense because it's so light. Like in principle, any atom or molecule can kind of want to go be part of another molecule, but they can't. But hydrogen is so teeny, it's just a proton. It can kind of be drawn over here. And it actually happens kind of so strong, and it always happens in a line, that it can become a reasonable bond that affects chemical structure. So hydrogen bond, 4 to 100 kilojoules per mole. So we do our toy model for cholesterol. What to think about? Hydrogen bonds is electrostatic. And let's see, there's a big range there because it really depends on if they can align well or not. Other groups other than oxygen seem to do it with hydrogen. It's a big range. And then the third kind, there's only 3. The third kind is van der Waals forces. So these occur between anything. So let's think, what is the simplest, most inert molecule that we have? Helium. The first noble gas, helium. So the electrons are very happy, they don't want to interact with anything. Right? Hydrogen's the simplest, but it reacts with itself to make H2. Helium is just helium. So you have these 2, and they're all the same size. I guess that could be an isotope or something. So 2 identical helium atoms. Like this. No reason to interact with each other at all. Right? Totally chemically inert, but they will actually be attracted and can even bond together because you have fluctuations of charge in atoms and molecules. So basically, this is made up of 2 positive protons and electrons, and very briefly, you can have a fluctuation where that side's a little bit positive. And that will induce a little fluctuation where that side's, this has a little negative, will induce a positive there, and that lowers energy and they're attracted to each other. So it's all based on fluctuations. So everything is attracted to everything, just like gravity. Well, not just like gravity. Not mathematical like gravity, but like gravity, everything's attracted to everything else due to these fluctuations. It's very weak, right? So all of these are weak compared to covalent bonds or regular chemical bonds. And even of these, this is the most weak. So like 0.5 kilojoules per mole. So the reason we had to go through that is in our toy model, we're going to say how deep are these wells. It's part of the model. Because we got to compare like thermal energy jiggling to that energy of the well, and that's what helps us figure out the time. Okay. So you may have heard of some of those. Pretty standard. There's others, but those are kind of the basics. Okay, so now we know what it's thinking. Now we have everything we need to know to make the toy model. Here we go. Toy model. The tubing is small, 1 by 1 millimeter. The tubing is long. What is long? 1 meter. So this orders of magnitude. 10 meters is also long, but that's too long for the lap, right? Lap, I mean, it's bigger. 10 meters would be ridiculous. So I'm going to say 1 meter. The next thing we got to make up in the toy model is how frequently do we hit these things? What's the density of sticky points? The way it really works is you just coat the walls of the tube with some rough material, and it's polymer or something like that. You can't really go by the generic properties of a rough material to get a length scale. But the one thing we do have is the size of a molecule. Right? So a cholesterol molecule, like So the sticky parts probably have to be farther apart than 2 nanometers. We won't have a lot of them. So we just say, how about 100 nanometers? Sounds good. Right? So the toy model, as long as we get the order of magnitude right, that's all that really matters. So we're going to say a sticky spot every 100 nanometers. 100 nanometers, or about 50 molecules along. So that's not the spacing between these. So now we have that number. Okay, so that's our device. We built it. Now we have to flow liquid into it. Because we're trying to get retention times. So we're trying to figure out how long will it take the liquid to go through. So we have to have a flow rate. So I just looked up a bunch of chromatography systems and said, what's the typical flow rate? Typical is 10 mils per minute. 10 mils per minute. So mil means milliliter. And we want to do this in meter type things. So that's also equal to 10 centimeters cubed per minute. All right. Now we want to turn that into a velocity. Like how fast is it going? So what we need to do is the velocity of the flow, this is the flow rate, the volume, the flow velocity is basically that number, 10 centimeters cubed per minute, divided by the cross-sectional area. So I'm not going to do the geometry for that to you, believe me. So to turn that flow volume into a speed, 10 divided by that, and that is 1 by 1, or 1 times 1 is 1 millimeter cubed. We're really just trying to get this down to a speed. We're not doing anything fancy. So the flow velocity, that, and then, there's a lot of, if this was a physics class, we would practice this a lot, changing units around. So I guess probably the easiest is to convert the centimeters. Okay, so what you do in your conversion, you multiply things by 1 a bunch of times, right? So you say 10 millimeters is 1 centimeter. Now let's do it again. 10 millimeters is 1 centimeter. All I did was multiply that by 1 twice, right? That's just 1. So then I just say, oh, millimeters are gone, 2 of the centimeters are gone. And suddenly I have 10 centimeters per minute, right? Oh, but let's get it to seconds. So let's multiply it by 1 again. Minute is in the bottom, so 1 minute is 60 seconds. There we go. So what we're doing is multiplying 10 times 10 times 10 is 1,000 over 60 is 1,000 over 60. We got it down to centimeters per second. Meters, yeah. That's 1,000 over 60 centimeters per second, or 100 over 6 centimeters per second, or if we wanted meters, 1/6 of a meter per second. Okay, sorry, this 1/6 meter per second finally. That's a full velocity. I didn't think that to be so weird at all. Okay, so now, what we know is, ignoring the sticky parts, just based on flow, just shooting the liquid through and ignoring any molecule sticking, that's how fast it's going to go. 1/6 of a meter per second. So now we could use things that could be on the exam to figure out how long will it take for the liquid to go through and doesn't stick. Which equation is this? D will be T. All right, so we know it's going to go a distance of 1 meter. V is 1/6 meter per second. So how long? 6 seconds. So now we know. It's a simple kinematics of a fluid flow. I haven't told you this, you would have to have been given this. We know that those molecules will fly through in 6 seconds if nothing sticky happens. So now, what we're going to do is add a sticky part and see what it does. All right, this is the exciting part. Just I know it's hard to tell, but this is the exciting part. I always let people know the exciting part comes. Sometimes it's also exciting. It's hard to of course not. All right. So let's now figure out for a molecule to get stuck, it's going to take 6 seconds plus the amount of time to escape each well. Okay, so how long to escape a well? All right, so you may recall that we talked about this last time. If you have a particle in here, it's kind of bouncing with some energy. It really comes down to two energies. There's K, that's the rate of escape. And if you want to know how long, you just invert that. Right? So that's an inverse second, so you just turn it over, and that's how long it would take it to escape typically. Then there's A. It has this factor in front. That's the attempt frequency. It's kind of a fudge factor, but don't worry about it. I'll give you a number. That's how often does it actually try to get out of the loop? You know, so if it's shaking around, how many times does it kind of approach the edge of the well to get out? And then there was the magic part, the exponential part, which is the ratio of e to the minus, I'll just go with a traditional EA label, over KBT, K subscript BT. That's what you would see in a textbook. Okay, so EA is the depth of the well. It's usually called the activation energy, but we're not really using it that way. But I'll still use EA. For us, it's more like the depth. So this is the depth. And then this is room temperature energy, which is, like I said before, 2.5 kilojoules per mole. Those are the, comparing those two numbers is the important part. They're in the exponent. Okay. So all we got to do is come up with these two numbers. Right? The temp frequency, the depth of the well, and we can calculate the time, see if it makes sense. Roll 20. Okay, so what do we want to do first? I think first we'll do the attempt frequency, because all I have to do is tell you a number, 10 to the 7. I can kind of justify it with that movie, right? It's really just about sort of like gas phase, how often molecules bounce into each other. So you can kind of just take their energy, their room temperature, and their density, and how many of them there are, and you can estimate numbers. So like water molecules bounce into each other, you know, about 10 to the 12 times a second. If you were to look at this movie, which I guess, if it's a way of calculating it, if you were to watch these droplets bouncing around much slower, right? They're like a few times a second, but they're much bigger. It depends on how big the thing is that it kind of jiggles around. So, molecule and sort of the organic molecule range in a fluid or a gas, 10 to the 7 is a typical number to use. So really what we're measuring is those 10 to the 7 attempts. This number says how many of those actually let it get out. This number will be less than 1. Right? So that'll bring the number down, and then you know how fast it can get out. Okay, so then once we have that, we'll just throw in 10 to the 7. Now it's the depth of the well. This is the big question. What do we put in? Do we just make up a number? Can we base it on anything? We can. Base it on, we're going to detect 2 steroids. We're going to try to resolve. I don't like the Dickinsonian paper. They're not detect, we're going to distinguish. And we'll see if they go through our chromatographer at different times. Let's see, so 1, oh god, I have to draw. Let's see, so ring. Tail, there's another one there, and then it has like 2 at the side, okay? So that's kind of like cholesterol, except we're saying the OH is gone, there's the 2 carbons here, who cares? You have 1 extra carbon there in the chain of the 2 things. So that's pretty close to cholesterol, except we're saying that that oxygen is gone. Okay, so let's detect that. So this is cholesterol, without OH. Then let's detect the same rings, same thing here, except it's missing one carbon. One little methyl group is missing. Same, missing, So kind of like we saw in that paper, it was amazing. They could tell like things like which side is the carbon, which side is hydrogen on. Like they could see all this from chromatography. So we want to see if you can really see these teeny little differences. So now we got to think about what is the depth of the well we're going to put in our model. Okay. So there were three things we talked about. There was electrostatic. Okay. So is the cholesterol charged anywhere? No. No, I didn't describe it in good enough detail. This is a chemistry class. But there's no functional group on the cholesterol that's going to be charged. The hydroxyl group, that oxygen could be charged, depending on the pH and all that kind of stuff, the water, but we took that off. So basically there's nothing charged. So there's no electrostatic contribution to the well. So forget electrostatic. The next was hydrogen bond. So no electrostatic. And the next was hydrogen bond. And I'm going to say there's no hydrogen bonds. Okay? Now there's tons of hydrogen. So you might say, well, there's so much hydrogen. Surely, I mean, there's 2 hydrogens on every carbon has 2 or 3 hydrogens on it. But hydrogens bonded to carbon don't hydrogen bond very much. They're very tightly bonded to carbon. It's usually hydrogen bond, or hydrogens attached to oxygen or nitrogen or some other molecule. Hydrogen bond carbons or carbon hydrogens don't really H bond. No hydrogen. So it seems like we're headed to a problem here, except now we have van der Waals. Everything van der Waals. So that's a very ubiquitous kind of a thing. Everything can have its charge fluctuate. So if we think back, there was 1 kilojoule per, well, it was 0.5 to 5 kilojoules per mole for van der Waals. Let's just say 1. And then, how many van der Waals bonds or van der Waals interactions could there be? So we'll get it and say, well, there's 74 atoms in cholesterol, more or less. So maybe it's 74. But typically, if you have a molecule, like here's your cholesterol molecule floating around chains like this, it's not that every atom is going to, it's typically kind of like the surface atoms. You got to get really close for a van der Waals bond. So if you had like some surface you were bonding your molecule to, you wouldn't really add on the van der Waals of every atom. You have the van der Waals of the atoms that are actually going to get really close. So that means the carbon skeleton, forget about the carbons, it's just the hydrogens. Okay, so if it's about 70 atoms and every carbon has 2 hydrogens, then that's like 40 hydrogens, more or less. So say, okay, so here we're doing van der Waals. Oh, we have 40 hydrogens, but it can't really do both sides at the same time. It's really only this hydrogens on one side that are going to significantly interact with the surface with a sticky spot. So I'm going to say, let's call it 20 hydrogens. And since each one we're saying roughly 1 kilojoule per mole, let's call this thing 20 kilojoules per mole. So there is our well depth, our activation energy. If we want to use the term, it's not really relevant, right? 20. So we'll see what that does with the toy model. But then what about the other one that's missing the methyl group? Let's just take one off. Let's call it 19, right? So the full cholesteroid is here, here. Let's call this 19 kilojoules. Sure. Because let's say it's missing 1 carbon, so you can say that's 3, that's a methyl group, so it's 3 hydrogens, but 2 of them would be there for the carbon, so let's just call it 1. These are all very rough numbers. Toy model, we should just say 10. We're trying to be a little more precise than that. Okay, so now we're ready. This is the big moment in our lives here. We're going to plug it in and see what we get. All right, here we go. Should be some torturous homework problem. Let's see, so let's do K. So let's say for the, I'm just going to call it left molecule. The left cholesterol. The one that's the full thing. So we just say, okay, what is the rate? It's A, which is at 7, E to the minus. EA was 20 kilojoules per mole over 2.5. That's all you're going to do. And the K you get when you do that, I think I have more numbers than that. The K you get when you do that is, so you can see that's like 8. It's like e to the minus 8, which means 10 to the 7 over e to the 8. The e to the 8 is a big number, because it's like e is 2.7, so like 2.7 times 2.7 times 2.7, 8 times. So it brings us 10 to the 7 way down, but not all the way down to 1. It's 3354. Okay. So remember what that is. That's inverse science. So K is a rate. What that means is, if you just let this thing do it over and over again, put it in a well, let it get out, put it in a well, let it get out. You can get out this many times a second. So we want to make that a lifetime. Lifetimes in physics are usually called tau. That would be 1 over K. So 1 over that is 0.3 milliseconds. 0.0003 seconds. 3 milliseconds. Okay. So that's pretty short. Because we're trying to do a retention experiment here, it's going to take it 6 seconds just to get through the tube. And now we've only slowed it down by 0.3 milliseconds. Of course, you know, the issue is there's 10 to the 17th spots. What we're going to do is now say that's for 1 spot. So we say, how many sticky spots were there? There were every 100 nanometers. So the number of spots in our model was 1 meter over 100 nanometers. It's 10 to the 7. These both make 10 to the 7 sequences. I didn't really mean that. That's what you get. So multiply this by 10 to the 7. So let's see that. So the retention time equals 6 seconds. The original, whatever it takes when it's not in the thing, when it's just flowing through, plus 10 to the 7 times 0.3 milliseconds. Because it gets stuck in each one. All right. So of course you got to convert milliseconds to seconds, blah, 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 and you get about 3,000 seconds. Is the retention time. What is that in minutes? 15 minutes. Okay, so we just found, through our rough little estimates, that, is this going to wake up? And so we can look and compare that the solution would fly through really fast if we just let it go however it wants. With our silly little toy model, we found it would flow through in about 50 minutes. Okay. And now we can look at this chromatography of Dickinsonian again more carefully. So remember, when we looked at this, we discovered they don't show you the mass spectrum, all the mass spec stuff. They're showing you the chromatography of different mass spec peaks. And you can see the x-axis is always in minutes. And we actually nailed it. Right? The real answers were like 60 minutes. We got 50 minutes. So that's shockingly close for a toy model. Okay. Shouldn't be that close. You probably think, I spent my whole weekend tweaking these numbers to make it come out close to the pool. I didn't, okay? I don't care that much, I assure you. I care about this class. But the point of a toy model is not to sit there, mess with the numbers and try to get the right answer. It's just to get the right order of magnitude of the answer. Okay? So just pretty lucky, though. It actually didn't come out right there. So what that tells you, though, is that all the numbers we did are roughly right. I mean, they all, one order of magnitude will not be affecting another order of magnitude. But the main thing, I think, we put in physically that makes sense, really, the critical number is this number. Getting a roughly the energy that you get when you bond, and then comparing it to KT. I think the 100 nanometer spacing is ridiculous. I have no idea. That was just totally made up. And this number is also pretty rough. But anyway, so now you can see, okay, so this very simple description kind of makes sense. But what about the other one? So now we've shown, yes, we understand chromatography, we understand the whole thing. Now do we understand how they can see these teeny differences when all they've got, is a hydrogen on one side instead of another side, and the only difference is going to be like a single van der Waals bond. So let's run the numbers real quick. Right. It's the exact same calculations. I won't write all number down. It's K equals 10 to the 7 e to the minus 19 kilojoules per mole over 2.5. All we did was take away one little van der Waals bond and drop from 20 to 19. But it has a big effect. This is where I didn't quite nail it. Okay, so let's see, K is going to just give you some, if you go through it on your own here, I know you will, then you're going to get that the tau is down to 0.0002 seconds. And when you multiply it all out, the retention, 33 minutes. So it comes out faster because it's having a weaker interaction with the chromatography column. That makes sense. But for us, it kind of cut the time in half. And they found with minor changes in the chemistry, it was really just changing the time by a minute or so. So this, our toy model, is not as accurate. But it does show that just one van der Waals is enough to make a big difference when you're interacting with a lot of things. So this would be a case we really wanted to understand it. We go through and start tweaking numbers, and my guess is there's less spots where it interacts. That might be the difference, I'm not sure. But it also shows you the significance of this part, right? It's really this exponential that makes such a small difference there below and such a big difference in the time. It also shows you that this method is probably very sensitive to temperature. Because you change that temperature, your 2.5 changes. Also has a huge effect. So this is what you can do with this system. Start to look at it, see where it's sensitive. This probably tells you we probably need to have a temperature regulation in this experiment. You know, we can't just have this thing sitting in the sun and doing chromatography. So these are the kind of things you can learn for the toy model. And now I feel like we understand this plot definitely better than I ever thought we would. Because I thought of the idea of doing this toy model Friday. And I did it last night. That's the other great thing about toy models. It's not like it's a big theoretical physics problem. Cool. Okay. We finished mass spectrometry.